Right, we're going to continue on through our whistle-stop tour through some of this preliminary content. And in this video, we're going to take a quick look at some baseline stuff we're assuming that we pretty much already know about, in particular, inequalities and functions. We established already that we looked at the rational numbers and established that they were an ordered field. That means we could put an ordering on them, so things like A is less than B and B is less than C means A is less than C, that kind of thing. It all sort of makes sense. So let's just establish some things that we know about inequalities, and I'll state them as theorems because it's not that hard to prove and it's a good exercise. So what I'll do is I'll state a theorem about these things, and then we will look at proving one of them. So here it is. We've got this theorem. Essentially, these are properties of inequalities that you will have done before, maybe even in high school. First one is that one I just mentioned. If A is less than B and B is less than C, then it follows that A is less than C. Second one says that we can add a constant to both sides of an inequality, no matter what the constant is. Notice I've used this symbol R here for real numbers. We haven't really quite established the real numbers yet, but I'm just going to sneak that in there a bit early because we all sort of intuitively get what's going on with those. So for the time being, if that makes you uncomfortable, we can treat that as a rational number. That's fine. The third one's what happens if you multiply by a number through an inequality, and is that familiar rule: if you multiply by a positive number, the inequality remains the same direction, and if you multiply an inequality by a negative number, part 4, then the inequality has a reversal in direction. Okay, so what we're going to do is we'll assume, just for the sake of argument, you can fill in the details yourselves later if you want, we'll assume that we've proven the first 3 parts, and we'll prove the last one. So let's just remove those. So proof of 4, assuming 1 to 3. Okay, so we have to do this statement. It says if A is less than B and C is less than 0, we need to then show that AC is greater than BC. So we'll do what we call a direct proof. So a direct proof is just a simple one where you start with your hypothesis, which in this case is this part here. If A is less than B and C is less than 0, that's a hypothesis. And we try and just make logical statements that directly lead to our conclusion. So direct proofs are kind of the best ones you can do. They're the nicest form because they don't require anything strange. So typically speaking, if you can produce a direct proof of something, that's the way to go. It's only that some problems are pretty hard to do that with, and we have to attack them slightly less directly. So we're going to assume our hypothesis is true, and we're going to try and come up with some statements using facts that we already know to derive our conclusion AC is greater than BC. Okay, so I'll start by writing down my hypothesis. A is less than B, and C is less than 0. So I'm going to use this implication symbol to mean this implies. Now I'm going to write down a new statement that I can justify based on my hypothesis combined with facts that I know. Now I can see that in my conclusion, I've got these product terms AC and BC. It looks quite a lot like part 3, so what I'm going to try and do is see if I can manipulate what I've got here so that I can use part 3 of my theorem. So I'm going to multiply through by C on both sides, and then I will see what happens. So this implies A times C. Hang on a minute, we don't know what to do with negative numbers yet, but I can make a positive number out of my negative number by multiplying through by negative C. So I'm multiplying both sides of this by negative C. Negative C is a positive number, so I'm allowed to do this because part 3 says that's a valid thing to do. Right, so this statement here, I've now got an inequality. I'm just going to expand out those brackets, so I'll have another implication. Now notice this arrow here, it actually applies to this statement that I just did, not the one on the left. So what we're doing is we're building up a chain of these implications. So what we should end up with at the end is a statement where the first hypothesis here should lead to our conclusion at the end, all things going to plan. Right, so this will become negative AC is less than negative BC. I'm after AC is greater than BC, and I can get that quite easily here by just adding a constant to both sides. I'll just note which part of the proof I used here as well. So I'm going to add the constant AC plus BC to both sides. It's just a shortcut for adding AC to both sides to cancel off the negative one on the left, and then doing the same thing on the right. So I'll do it all in one step. So this implies I'm allowed to add constants, because that's what the second part of the theorem tells me. The negative AC plus BC is less than negative BC plus AC plus BC. This is by 2. And then we can cancel some things off, because the ACs will cancel out. I'll get BC is less than AC. And that is actually what we're after. It's just written the other way around, as required. So what you can see is that we started with our hypothesis. We used justifiable steps to just go one step at a time through. Each time we're just using right ways arrows to show our implication. They may actually be left and right arrows sometimes, but because we're just trying to get from point A to point B, it doesn't actually matter. So long as the implication at least goes to the right, that's fine. We justified the steps where necessary. Now this is painstakingly simple compared with what you're going to be doing later, but it's good practice for sort of setting out a template for how we illustrate our proofs. Sometimes the justification for a step may actually require a sentence of writing in between steps. That's absolutely fine, so go ahead and do that. But we've proven now our fourth part of our theorem, and you can prove parts 1 to 3 if you so desire. I just note the theorem numbers in the reader are 1.2.1 through to 1.2.4. Let's do another example. Here's the familiar one, that is when you take reciprocals of fractions, then, well, if they're both positive, then you reverse the order of the inequality. So if A is less than B, both A and B are positive, then 1 over B is less than 1 over A. So when I take my reciprocal, I reverse the direction of the inequality. You could also write that as 1 over A is greater than 1 over B, which is both greater than 0. Alright, so to prove this, we can do a similar thing. First off, we'll note that if A is positive, so is 1 over A, and so is 1 over B if B is positive. So note 1 over A and 1 over B are automatically positive. So we don't need to worry about the 0 particularly, because that's not we're not going to end up with anything less than 0. So I'm going to start with 0 is less than A is less than B. This implies, now I'm just going to do the effect of dividing through each side by A and B. I'll do it one at a time this time. So I'm allowed to multiply by a scalar, a positive scalar. That's one of the parts of our previous theorem. This implies that 1 over A times A is less than 1 over A times B. Multiplying by a constant positive number doesn't change the direction of the inequality. This in turn implies, just tidying it up, that 1 is less than B over A. Do the same thing, we'll divide through both sides by B. 1 over B, again it's positive, so inequality stays the right way around, is less than or equal to, less than 1 over B times B over A. And just cleaning that one up gives us 1 over B is less than 1 over A as required. So one more common one that you might have to use for some reason is if you want to multiply two inequalities together. So let's quickly state that too. I'm not going to prove this one because I think we've had enough of proving inequalities for the time being. So this one just says if I've got two inequalities, first part says I can add them together and I can just add the corresponding sides and the inequality is preserved. Again, if you want to prove this, it's a fun exercise to do. And the second one says if I have two inequalities involving positive numbers, then I can multiply them together. Now, it's not that much more difficult if you have some negative numbers involved. You just have to be a little bit careful about thinking about what's happening on either side of your inequality as you multiply things through, and reversing inequality signs should you so desire. Onwards and upwards. Next up on our list of revision items is functions. So we're going to look at a function taking elements from a set A and producing elements in a set B. And our definition is that a function is a rule or a mapping that takes each element from A, so it has to apply to anything in A, and associates with each of those elements a single element, f of x of B. A little bit of notation, we write f takes A into B. Okay, so this set A is called the domain. we have the range of A is the set of all f of x where x is in the domain. Or we'll often just write it as f of A because it's more convenient. Little quick note, the range of A is not this whole set B itself, but it's contained within it. So note f of A is a subset of what's called the codomain B. You can even write that on there if you like. Not a term we use that often, but this set actually has a name. It's called the codomain. Alright, so we've got our function taking us from our domain into our range, and our range is the set of f of x's where all of the x's are from the domain. A couple of things about functions. We say that a function is one-to-one if given two distinct elements in A, it produces two distinct elements in B. This means that we can't have two different elements in A that map onto the same value in B. Okay, so every distinct elements have to map onto distinct elements. We can't have any, like, if you're thinking of continuous functions, which again we haven't actually introduced yet, but they can't sort of flip over and have a peak where you've got two y values the same on either side of it. That's what a one-to-one function is, and again we'll touch on this more when we actually need it. Second thing is onto, that comes with one-to-oneness. A function is onto if given any value in our codomain or our output set big B, we can find a value of A in our input set big A that maps to it. Okay, so we touch every possible element in our output set is mapped to by something from our input set. There's no empty spots in our coverage. So there's one function that we'll use so much that we will actually dedicate a little bit of time to it right now, and this is the absolute value function. So it's defined relatively simply. The absolute value of x is defined to be, well, the definition depends on whether it's negative or positive, x if x is greater than or equal to 0, or if it's not, negative x if x is less than 0. Okay, so if we were to try to draw a graph of this thing, it looks like this. It looks like x for the positive half, and it looks like negative x for the negative half. Okay, so a few properties that jump straight out. Property number one, for any real number, and again I'm using real numbers even though we haven't quite established them yet because this will all apply once we've actually set them up properly. It applies to rationals equally well. The absolute value is greater than or equal to 0. Okay, so absolute value removes anything negative and makes it positive. Property number two, if the absolute value of x is equal to some value a, which has got to be positive or 0 at least, then you've got two possibilities. Then either x equals a or x equals negative a. Okay, so in words, if I have the value, in pictures, if I have a value a here, then there are two possible values of x. There is a over here, and there is negative a over there. So whenever we've got an absolute value statement in an equation or an inequality, we need to break it up into two pieces and look at both possibilities. Likewise, quite often we'll have the absolute value of x equaling the absolute value of y. Then, again, we've got two cases. Either x equals y, or x equals negative y. So this also produces two things that we need to know. Okay, so how does absolute value behave under addition and multiplication? Well, multiplication is quite straightforward. So property 1 here is that the absolute value of AB is just equal to the absolute value of A times the absolute value of B. We'll use this one all the time to bring constants outside of things like square roots and stuff. just use the fact that we can break an absolute value up into a product of absolute values and do with the individual pieces what we like. Number 2 is a special case called the triangle inequality. This is what happens when we add inequality, sorry, not equality. The absolute value of a sum is not equal to the absolute value of A plus the absolute value of B, although it might be sometimes. It's less than or equal to the absolute value of A plus the absolute value of B. Okay, now I might get you to prove one or more of these in an assignment or something like that, but they're quite easy to verify just by looking at the different combinations of signs of A and B that you can have. Alright, so triangle inequality is something that we'll highlight because you will use this frequently, and there are a few different ways that it will show up. A common one is what we'll just do in a second. So a common thing that we'll often have to do is, if we've got numbers A, B, and C, so common usage, we'll take numbers A, B, and C. Again, they'll be real numbers for now. When we establish what real numbers are properly, we'll be able to use them. And we often do the following trick. If I've got the absolute value of A minus B, then a common trick is to introduce the third number C to break this up into pieces. So I'll make that equal to A minus C plus C. Okay, I've just introduced a 0, that's fine. Minus B. And now I'll use the triangle inequality to break that up into two pieces. The absolute value of A minus C plus the absolute value of C minus B. Notice the absolute value of C minus B is also the absolute value of B minus C. It's the same thing. Multiplying by -1 and using the multiplication property will show us that that's the case. So what this says is distance between points A and B is how we interpret this. Is less than or equal to distance between A and C, and the distance between C and B. And this is why it's called the triangle inequality. Because if, for the sake of argument, you just imagine now that we're not dealing with real numbers, but we're dealing with points on a plane, then this says the distance between A and B, this side of this triangle, is less than or equal to the sum of these two distances. In fact, let's make them different colors. So this says that this side length here is less than or equal to the sum of the other two side lengths, which is a basic rule about triangles that take any two sides and the sum of them is less than or equal, take any side and it's less than or equal to the sum of the other two sides. That's why it's called the triangle inequality. Okay, I want to do one more example with absolute values, and we're going to work much like a computer would if you were trying to prove something with absolute values. So again, this is not necessarily the way we'd go about working a problem like this in an assignment, but it's good to see sometimes where these things actually come from. So I'm going to start with the statement absolute value of x minus a is less than r. And if we use the distance interpretation that we just put on this problem before, this says I want to find all of the points x that are within distance a of r. Okay, now but if we want to actually formally manipulate this expression using our definitions and things, then this is equivalent to, well, we've got two cases. Absolute value is either equal to itself or a negative version of itself, depending on the sign. So it's either one of these two things, equivalent to the following. First is where the inside of the absolute value is positive, and in that case, absolute value of x minus a will just be x minus a. So that's one case. Or, second case is x minus a is actually negative, the inside of the bracket, in which case the absolute value becomes a minus x is less than r. Alright, so if we just have a look at this for a second, what does this say? This says, this first part of it says, if we just rearrange our inequality, we get a is less than or equal to x from this piece. And we'll make this one about x as well. X is less than a plus r. And down here, we have the opposite. We have, we rearrange this one for x. We get x is less than a. And here we get x is greater than, what will it be? It'll be a minus r. So we can see that our statements are equivalent to, the first one is two statements about x. So let's write down our first statement first. A is less than or equal to x, which in turn is less than a plus r. That's my first bracket. Or second one is that a minus r is less than x, which in turn is less than a. Now if you stare at this for a moment, you can see that these can actually be combined, because if we look at these different cases here, remembering this or just means one or other or both of these are true. If x is less than a, it's certainly less than a plus r. So we can get rid of the x less than a and just have the x is less than a plus r. Likewise, if x is greater than or equal to a, then it's certainly greater than a minus r also, because r is a positive number. And so these can be combined into a single statement. So let's put them together, and we'll start with the lowermost thing, which is a minus r is less than x is less than a plus r. Now this we pretty much could have written straight down, and so in practice, when you ever come up with a statement like this, you'll jump straight to this interpretation, but having the mechanical explanation of how this actually comes about using the definition of the absolute value function is actually a useful thing to have up our sleeve. Okay, now we could also write this as an interval, or x is an element of the open interval a minus r up to a plus r, i.e. set of points closer than r to a is what our inequality expresses. So we'll have one more short preliminary video after this one, just to wrap up some of our initial loose ends, and then we'll dive into some of the meat of the course. Catch you next time.